Hey, Coach Travis here, and what I want to talk to you about today is algebraic topology. Well, in particular, group presentations and topology. So like I said, my talk is about algebra and topology. And the other Dr. Kelm, she also talked about algebra and topology. But I would kind of say that her talk was maybe a little bit heavier on the topology and lighter on the algebra, whereas my talk is going to be heavier on the algebra and a little bit, when I get to the topology part, it might be a little bit light on the topology. So it might be a good idea to go back. You might want to go back and look at her video at some point while you're watching mine if things don't make sense. But you take our two videos and you put them together, and you got the Reese's peanut butter cup of 191 Tea Talks. So anyway, so here's what I want to do today. So I want to talk to you about what a group is in abstract algebra. We use these things called groups. What are those things? Why do we care about them? And I want to kind of do a fun example. And then I want to show you how you can actually make your own groups. So you can just from scratch, you can build groups might seem really weird and abstract, but there's actually a really easy way to just throw together your own group. It's really fun. And then you might say, well, okay, great, Travis, I can make a group, but who cares? But it turns out the groups that you make are actually very, very useful in topology, for example. So I want to go through all of that. Okay, so anyway, so let's see. So what the heck is group theory? So, well, if you think about mathematics, math is kind of all about sets. Everything we deal with in mathematics are sets. Sometimes there's sets of numbers, maybe there might be sets of symbols. Other times there might be weird things like sets of functions. But when you get right down to it, sets are actually kind of boring. And you say, what? And I say, yeah. Sets are kind of boring because they kind of just sit there. And you say, well, no way, Travis. This set here at the top, I love this set. It's the set of numbers. I can add numbers and subtract them. I can do all sorts of fun stuff with numbers. And these functions, I can do fun stuff with functions too. And I say, well, okay, yeah, but not so fast. That addition and subtraction thing that you talked about, that's not actually part of this set. Addition and subtraction if I'm an alien and I just look at this collection of symbols, there's nothing in there about addition and subtraction. So the moral of the story is just as a collection of symbols, this is kind of boring. It just kind of sits there doing nothing. But it's when you add the ideas of addition and subtraction to it that it gets really interesting. So anyway, so that's where group theory comes from. So the idea is that sets are much more interesting if we build in a way for the elements of the set to interact with each other. So let's see here. Yeah, so like for the set of numbers, we have fun with numbers because they can interact with each other by adding together. They can also multiply if you want to, and if you're lucky, they can divide. But let's try to keep it simple here, and we'll just worry about them adding together right now. And then the set of functions, as an example, if you have a one-to-one function, so these are bijective. If this is a collection of all bijective functions from the real numbers to the real numbers, if I compose them, if I take one bijective function and I compose it with another bijective function, does that give me another bijective function? Well, I'll let you think about that for a little bit, but it's not really that important right now. But the idea is the functions can interact by composition. And so anyway, so we got these things can interact with each other. But again, I'm emphasizing that the addition and this composition idea, they're not actually elements of the set. They're kind of outside ideas for how the elements of the set can interact. So anyway, so a group is that it's that basic structure. A group is a set. At its foundation, it's a set. But along with the set is a way to combine the elements together to give us just enough structure so that we can sort of do algebra, that we can do interesting mathematics with the elements of the set. So let's be a little bit more specific, but not too specific. So basically, a group is a set, like I said, and along with the set it's a way to combine the elements of the set such that, okay, so if you combine two elements of the set, then you get another element of the set. So that is combining two apples doesn't give you an orange. Well, that's kind of a terrible example, but the idea is you don't get anything outside of your set. That the set is self-contained. And then the other thing that we want to have is we want to have like a special element that we're going to call the identity. And that might seem kind of weird, but when we see our example, I hope it'll make a little bit more sense. And then every element has an inverse element. So let's look at the set of integers here. So the idea here is that, okay, so great, this is a set. So we got that taken care of. If you combine two elements, you get another element. Okay, so again, we're combining them by using addition. So that's pretty clear that, okay, if I take two integers and I add them together, I get another integer. All right, so we're okay there. And then let's see, there's this special identity element. So what the heck is Travis talking about with that? Well, what I'm talking about there is I'm talking about this 0 guy. Like 0 has a really interesting property. Like if I take any number and I add it to 0, I get back to the original number. So that's kind of why we call it an identity element. Is it doesn't change anything. And then so we got 0 is the special identity element in this set. And then every element has an inverse. So an inverse would be an element that you combine with another element to get the special identity element. So like 3 is an element of my set, and if I add a -3, so -3 is also an element of this set. And if I combine 3 with -3, then I get that special identity element. And that's true not just for the number 3, but if you give me any element in any integer, there's some other integer that I can add to it and get 0. So the moral is that the set of integers with addition, it satisfies all of these things. And it's an example. It's a kind of the prototypical example of what a group is. So now groups might seem sort of abstract and esoteric, but the fact is that in reality, groups are everywhere. Once you sort of learn what a group is, then you see them all over the place. So groups are behind the scenes in almost basically every math class: linear algebra, number theory, geometry, calculus. If you look hard enough, you can find groups in every one of those things. And not just find groups, but you can find that groups are like central to those things. But even outside of mathematics, groups are everywhere. For instance, the 24-hour military clock has a group structure in it, if you think about it. And also the set of moves that you can perform on a Rubik's Cube, that also has a group structure, because if you look at the Rubik's Cube, like you can rotate a face one way, you can rotate a face clockwise, or you can rotate that face counterclockwise. In her video that she did for 191T, the other Dr. Kelm, she showed you how the dog walking group can actually be used to distinguish between topological spaces. So we'll talk about that a little bit more later. So the bottom line is why you should care about groups is what groups do is groups allow us to do algebra in places where we might not even have numbers. So when we think about algebra, probably most of the time you think about numbers. But the fact of the matter is with group theory, you can do algebra anywhere that you have the proper group structure, and that's in a lot of different places. So I want to show you a fun example of that, and that's this game called Peg Solitaire. So the idea is you got this board, and it's got a bunch of markers on it in a certain pattern, and there's an open spot in the middle. And what you're allowed to do is you play this game and you're allowed to jump any one marker over another single adjacent marker and into an empty spot. So you've probably seen games like this before. And then whenever you jump a marker, you remove the marker that got jumped over. And then you keep doing this. You keep making these jumps and moving the markers around until no more jumps are possible. Until you can't do any more legal jumps. And the goal is to make the maximum number of legal moves, which basically means you keep moving until until you're able to leave just a single marker on the board. And if you're able to leave that single marker, if you're able to leave a single marker on the board, then like you win the game. But if you're able to leave that single marker in the very central spot, then you're a genius. So anyway, what we can do with group theory is, well, we can't actually tell you what moves to make, at least not easily. But what I can easily show you is that if you're going to win the game, you're going to have to leave the marker in one of these positions. So in order to win the game, the final marker has to be in one of these 5 spots. It's impossible to leave a single marker in a spot that's different from one of these 5. So we can use group theory to prove that. So here's how we're going to do that. What we're going to do is we're going to assign every spot on the board a letter X, Y, or Z. And we're going to assign, like in this picture here. So every spot gets assigned a letter X, Y, or Z. And so now what I want you to do is notice what happens when we think about when a marker in the X spot jumps over a marker in the Y spot. So for example, here's an X marker and here's a Y marker. So if I were to imagine this X marker jumping over that Y marker, then that X marker, is going to land in the Z spot. So the X marker is going to go away and it's going to turn into a Z. So when X jumps over Y, you get Z. That's what I'm trying to say here. And well, what about when Y jumps over X? So let's see. Well, if a Y jumps over an X, then you can see no matter where that happens, wherever there's a Y, if it jumps over an X, it lands in a Z spot. And you can see that everywhere on the board. And then just for another example, what about if Z jumps over Y? Okay, so Z jumping over Y gives me X here. Well, I can't do it there. Z jumping over Y gives me X here. So you can see that whenever Z jumps over Y, you get an X. So the moral is there's actually an interesting way to combine these elements. These letters X, Y, and Z, we can use this board diagram to sort of give us a group structure. We can give a way for these elements to interact. And so here's what we'll say. We'll define this operation, and we'll have a little arrow to mean jump. So like when X jumps over Y, you get Z. And when Y jumps over X, you also get Z. When x jumps over z, you get y, and so on. So what we got here is we've got a set, x, y, z, and now we have an operation on that set that combines two elements of the set to give another element of the set. So that's sort of the first piece that you need to be a group. But now, if you've been paying close attention, and what I've been saying has been, and you've been following what I've been saying, you'll say, wait a minute, Travis, what about this special identity element? And you're right that I don't have an element that doesn't change things. That whenever you do these combinations, things change. So we need to throw something in to have a bona fide algebraic group. We need to throw in another element. So we're good. Let's just throw in another symbol. We'll have it be the symbol 0, and we can think of the 0 move as being nothing moves. You know, if the 0 element means nobody jumps over anybody, it's just nothing happens. Okay, so now we've got this new set, and so the set is x, y, z combined with the 0. And what I've got here is I've got a multiplication table that kind of tells you how these elements interact. So for example, if x jumps over y, then you get z, just like we saw before. So you can see, if you study this carefully, this multiplication table summarizes what we saw in the previous slide. But also it has the 0 element. So like if 0 jumps over x, then x is still x. Well, because 0 means nothing moves. So 0 doesn't really jump over anything, but if I pretended it could, it just wouldn't change anything. So 0 jumping over anything doesn't really mean anything, it's just there. And you might, if you look at this multiplication table, you might also say, well, wait, what happens if x jumps over x? Well, if x jumps over x, the table says I get 0. Well, because and that in some sense that makes sense, because if you look at the schematic, it's impossible for x to jump over x, because an x spot is never adjacent to another x spot. So you can't have x jumping over x. So the fact that x jumping over x gives you nothing kind of makes sense, because it can't happen. So, but anyway, the moral is that what we got here is we've got a bona fide group structure. We've got a set of elements, and we've got a way of combining the elements, and we have an identity element. Oh, and we have inverses, that every element is its own inverse, because if x jumps over x, we wind up with that special identity element. All right, so that's a group. So now what we're going to do is we're going to do some cool algebra with that group. So you can check by looking at that table, well, what happens if like x jumps over y and then jumps over z? Well, when x jumps over y, you get z. And then when z jumps over z, well, that can't really happen, so that gives you 0. And so in this way, what we can do is we can sort of add up all of the markers on the board at any particular moment. So let me do a quick example of that. So suppose I maybe have a marker right there, and I have a marker right there, and I have a marker right there, and I have a marker right there. So let's see. So what would be the total value of that board state? Well, if I look at the schematic over here, this is a z, and this is an x, and this is a z, and this is an x spot. I'm just looking at the corresponding labelings. And so, okay, so the value of this board state would be z jumping over x, and then add another z, and then add another x. And let's see, well, z jumping over x gives me y, and then y jumping over z gives me x, and then x jumping over x gives me 0. So in fact, in this case, in this example, the value of this board state is the 0 element. Okay, so the idea is now what we can do is if you give me a board state, I can compute the total value of the board state just by adding up the x's, the y's, and the z's. All right, so then, oops, I need to clear all of this. Okay, so now let's look at what happens when you do a legal move. So yes, oh, I shouldn't have erased. But anyway, so let's suppose we have a marker there, and a marker there, and a marker there, and a marker there, just like we had before. So we said earlier that the value of this board was 0. And now what happens if we do a legal move? Well, okay, so this was a z, and this was an x. And so the only legal move I have on this board is, well, I can have x jumping over z, or I can have z jumping over x. Well, let's just pick one of them. It doesn't matter. You can try the other one at home. Let's have the z jump over x. So if z jumps over x, then, okay, well, z jumps over x and is going to then wind up in a y spot. And then, okay, well, when the z jumped, that means I need to erase that marker because it wound up over here. And then also, whenever you jump over a marker, you have to erase the marker. So the x got jumped over, so I have to erase that. So now my new board state is, we got a z here, we got a y there, and we got an x there. And so let's see. If you add those up, z jumping over y, jumping over x, well, you can go, if you think about that, you also get 0. So after a legal, if the board state started at 0, then after a legal move, the board state is still the board state's not gonna change. And so that's gonna happen even if this wasn't just 0. You know, feel free to play around with this board and experiment, and you'll see that the moral here is that anytime you do a legal move, it's not going to change the total value. So if the value started off 0, it's going to stay 0. If the value started off as x, then after the legal move, the total value is still going to be x. So legal moves do not change the total value. And all right, okay, so well then what? Okay, well let's think about what if we were going to actually play the game? If we were going to actually play the game, what would be the value of the starting board? Well, you can check. Well, let's see, x, y, z, that makes 0. Here's another x, y, z, that makes 0. 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 That makes 0, that makes 0, that makes 0, and that makes 0. Okay, so the only things I didn't highlight were these two guys. And there's an x, and there's a z, and x and a z make a y. So the moral is that when you start the game, according to the rules, the total value of the starting board is a y. And so now if you think about what we just did on the previous slide, we said that whenever you make a legal move, it doesn't change the value of the board. And so if the board state started at y, then whenever we make a legal move, we're still going to have a board state of y. And now think about winning the game. If you win the game, there's only going to be one peg left. And so whatever that peg is, it has to have a board state of y. Because every time we make a move, we still have to have a board value of y. So if you only have one peg left and the board state has to be y, then that means that your peg has to be in one of the y spots. So here I have highlighted all of the y spots. So if you finish with only one peg, it has to be in one of these red spots. Okay, but you might say, wait, Travis. I thought if you go back in the video, you might say, wait, I thought you said there were only 5 possibilities. But the way you've got it shown here, it looks like there's like I can't count 10. No wait, 11. It looks like there's 11. So what gives? Well, it turns out we can rule out some of these because, like, let's look at this. Let's look at this spot right here. So that is a Y spot, no doubt about it. But by symmetry, if you think about the board is completely symmetric. The way you play the game doesn't matter which way you move the pegs around. So if you could end with a peg on this spot, then by symmetry, you would be able to end with a peg on this spot also. But this spot is an X spot. And we just decided previously that you can't end on an X spot. So that must mean we have to rule this one, even though it's a Y spot, it's no good. And similarly with these other ones, that one's no good. Let's see, yeah, that one's no good. That one's no good. That one's no good. And you can use these symmetry arguments to rule out these other ones. So the moral of the story is that the only real ending states that you could have if you want to win the game. If you want to win the game, the peg has to be in one of these 5 spots, because these are the only spots that are Y spots and that are not symmetric to other spots that are X's or Z's. And that's basically the end of the argument. That was supposed to be a fun example of how groups can be used. That what we did there is we sort of did algebra. We added things, but they weren't even numbers. When we added, what we were really doing was we were doing jumping pegs over other pegs. So that's a really kind of a cool thing. And that, to me, that's what's really fun about mathematics is using mathematical ideas in places that have nothing to do with numbers. Because, numbers are great and all, but there's more to life than just numbers. So like I've said already, groups arise naturally in a whole bunch of different contexts, like with the Rubik's Cube or with this peg solitaire game. But I'm kind of more of a mad scientist kind of type, and I wanted to make my own groups. I just want to get into my laboratory and just invent groups. And is that possible? And is it interesting? So I want to talk about that next. So here are instructions for how you can easily build your own algebraic group. So first start with let's keep it countable, any countable set. So just to keep it simple, let's just say take the set AB. And then what you can do is, okay, so I need a way to combine these group elements. I need a way to combine the A and the B. So what we do is we just make words out of them. A and B are letters, and again, they don't have to be real words. These are abstract words. You just make words by stringing together A's and B's. Okay, but wait, not so fast. To be a group, you also have to have a special identity element. Okay, so we'll use like the empty set to represent that identity element. And you also have to have inverses. So if you have a letter A, then you need to have an inverse of A. So I'll denote that by A bar. And then if you're going to have a B, you need to have an inverse to B. And we'll denote that with B bar. And so basically then what your group is, the set for your group is the set of all words that you can form using the letters A, B, and A bar and B bar. Oh, and along with this empty word. So you can see some examples right here. And so this is, well, anyway, we'll talk about this in a little bit in a minute. But you should say, wait, you're not done yet, Travis, right? Because how do you combine? How do you combine words? Because that's what a group has to have a way of combining elements. So if this is my collection of elements, then what we need to know is, well, how do you combine them? And so the way we combine them is we just smash them together. So if I have this, so this is a word that's in my set, and this is a word that's somewhere in this set. And so to combine them, I just mush them together. And this is another word, so this is going to be somewhere in this set. So what we got there is this is a bona fide group structure. We got a bunch of elements, and we have a way of combining them together. We have a zero element, an identity element, and we have inverses. I mean, again, you'll have to trust me a little bit. I'm not showing you all this, but it's true. And this has a special name. This is called a free group, and it's a free group on two elements. So we could denote it by F, capital F of AB. So all right. So, but this, when you get right down to it, this is kind of an unruly group, because it has, I mean, this group has infinitely many elements in it. And they're all they're kind of, you know, they're not nice. They're mostly, I mean, you've got elements in here that have thousands of letters in them, and the letters are all over the place. And so this, I mean, this is a group. There's, you know, it's an interesting group. But it's really, really quite complicated. So you might say, well, is there any way I can build a group that maybe has finitely many elements in it? That's not so crazy and doesn't have words that have lengths in the thousands? And the answer is, yeah, you totally can do that. What you do is you kind of just specify some rules. You say, okay, I'm going to declare that certain words are actually zero in some sense. I'm declaring that certain words are equal to the identity, and then you let algebra sort things out. So let me show you in an example what I mean by that. So we'll start with the free group like we did before. So we have all these terrible long words. But now what I'm going to do is I'm just going to declare the following. I'm going to say the following words are equal to the identity. And again, this is just an example. So you can pick any words you want depending upon how the spirit moves you. But just in this example, I'm going to say AA is equal to 0, and BB is equal to 0, and AB is equal to 0. And so the notation we'll use for this is we'll say A, comma B, and then followed by AA, BB, and AB. So that's basically saying take the free group on A and B, but then declare that these three words are actually equal to the identity. So it turns out if you do that, a lot of really magical things happen. So I claim that this new group that I formed actually only has 4 elements in it. And so this is a big difference, right? Because previously my group had infinitely many elements. It had words. It had words in it that had hundreds of letters. But as soon as I throw in these 3 new rules, then I get only 4 elements left. And you might say, wait, how is that possible, Travis? And so here's a quick example of kind of how that works. All right, so let's take a look at a quick example here. So if I take one of these big old words from the previous slide, maybe something like, AB, AA, B inverse, A inverse B. I claim that this can actually be reduced to one of these 4 things here. And how does that work? Well, the idea is, remember what we're doing is we're declaring that each of these things is basically nothing. So whenever I see one of those things in this word, I can make it go away. So for example, here's an A and an A. So those can just go away. So I get AB, and then there's the B inverse, and then there's the A inverse, and then there's the B. And now B and B inverse, those are inverses. So when they're next to each other, they always make 0, or the empty set. So, B inverse, that's always equal to the empty set. And A inverse, that's always equal to the empty set as well. So these two guys can knock each other out. And then we get A and A bar. And then there's a B. And hey, and here's an A and an A bar. So that makes 0 or nothing again. So we just wind up with B. So as soon as we impose these rules, it turns out we can reduce down to this crazy word here just reduces down to this simple letter B. And now in that example, if you're sharp-eyed, you'll say, hey, Travis, in that example, you only used this identity. And you might say, so do we really need these other two? And the answer is, well, I picked sort of an easy word so things didn't get too complicated. But in order to reduce all crazy words down to just one of these 4 things, you need all 3 of these. So anyway, so the moral is what we have now is we have a way for you to create a group and a way for you to sort of tame the group and, to make the group not necessarily completely crazy, to put in some rules to make the group a little bit more well-behaved. All right, and so what does this have to do with topology? So in her talk, Dr. Kelm told you how the fundamental group, which was what she called the dog walking group. So the dog walking group of a space can be used to tell when it is impossible to bend or stretch one topological space into another. So for example, here's a torus and here's a Klein bottle, and one might wonder, if I can bend and stretch these things as much as I want, can I bend and stretch the torus so that it becomes a Klein bottle? And that's just a good question. If I can bend and stretch this as much as I want, maybe I can do it. It's hard to say, but you can use topology and algebra to show that actually it turns out you can't. And how it turns out this fundamental group is related to what we just did. All right, so it turns out that the dog walking group, or the fundamental group of a cell complex that you build like you build the torus, is actually equal to a group presentation that's determined by how you put the cell complex together. Okay, so that's a lot of crazy words, but let me show you what I mean. So if you want to build a torus, what you can do is you can take a piece of paper, and then what we'll do is we'll start by gluing the left side to the right side so that these arrows line up. So we're going to glue the 1 to the 1 so that the arrows match up. And then now we're going to glue the 2 and the 2 together so that the arrows match up. So if you do those gluings, you get exactly a torus. And it turns out that the dog walking group of the torus is this group right here. That it's the symbol 1 with the symbol 2. And then we say that the word 1, 2 bar, 1 bar, 2 bar, just 2 is equal to the 0 word. And what I want you to notice, what's really cool here, is where does this come from? It might seem to come out of nowhere, but if you look at this piece of paper where we did the gluings, if you read around the border, look at what, if I start here and I read around the border, look at what I read. First, I read a 1. Then I read a 2, but backwards. And then I read a 1, but backwards. And that's what the bars are about. And then I read a 2, but in the correct direction. And there's a 2. So the moral is that to get these do-it-yourself groups that I told you how to build with group presentations, it turns out that those are exactly the dog walking groups of the complex you built. So anyway, I think we probably should wrap things up there. And so the moral of the story here is that groups are very important in science and mathematics, so important that we have an entire course, that's Math 151, that's devoted to talking about groups. But what they probably don't talk about so much in 151 is group presentations. And even more interesting is the groups you build, these do-it-yourself groups that you can build yourself, are actually a super interesting topic in topology, because these do-it-yourself group presentations, they are the fundamental or the dog walking groups for the cell complex that you're putting together. So if you're at all interested in algebra, and in particular how algebra can be generalized to deal with situations that don't involve numbers anymore, like topological or geometric applications, then group theory and group presentations are a really interesting area to do research in. And I hope that stimulated your curiosity and makes you look forward to taking Math 151 and learning more about algebra. So thanks for listening.